All right, guys, so last thing here, last thing in 5.2 we want to look at about the graphs of polynomial or of rational functions, and it's something called a hole. There can be a hole in the graph, and here's what I mean by saying there's a hole in the graph. Let's look at the graph of f of x equals x plus 5. It's a linear one. It's pretty easy. It looks just like this. Here it is. It has a y-intercept of plus 5, so 1, 2, 3, 4, 5. Has a slope of 1, so it would look something like that, something like that. There's a graph of f of x equals x plus 5. Now what I'm going to do is I'm going to mess it up a little bit, and I'm going to multiply the whole function. I'm going to multiply x plus 5. I'm going to multiply it by 1. Okay, but I'm going to write 1 in a funky way. I'm going to write it as x minus 2 over x minus 2. Because that's 1. Same thing on top, same thing on the bottom, right? What I'm going to end up is a function that says f of x equals x plus 5 times x minus 2 over x minus 2. So I kind of made it look a whole lot nastier, a whole lot more messed up. Now here's the thing with this thing though. If you look at this and you look at this, this should be the same as that one. I mean, this expression means the same thing as this expression, because if I were to like reduce this fraction, I could just cross these off. I would divide by this. If I didn't know how to graph this and I plugged in some values for x, if I plugged in, let's say here I plugged in 0 for x, I'd get 5. If I plug in 0 for x here, I would also get 5. And the reason is because whatever I get here, whenever I get here, I know I'm going to multiply by whatever it is, but I'm going to divide that out. So that's going to cancel out. And if I plug in 0, I'm still going to get whatever I got up here. I'm still going to get 5, no matter what happens. Try it, and you'll see it works. And that'll work just fine. So this graph is behaving exactly the same as this. If I reduce this, if I cross these out, I'm going to get f of x equals x plus 5. But there's a problem. Okay, if I just reduce it and say, okay, well, this is the same as saying f of x equals x plus 5. Remember, I'm just kind of going to stop here. So let's say we started here. We had x plus 5 times x minus 2 over x minus 2. If I just cancel these out and say, okay, yeah, I'm good, there's a problem with that. All right, and the problem is when we have this x minus 2 on the bottom, now we've messed with the domain. Now in this one, we're not allowed to plug in x equals 2. We're not allowed to put 2 into this function. We are allowed to put 2 in here. There's no limitations on us here. All real numbers is what we can use for the domain up here. But down here, because of this x minus 2 on the bottom, we have limited ourselves now. And now we're not allowed to use x equals 2. So to say that this is exactly the same as this would be wrong, because it is the shape of the graph is going to be pretty much exactly the same, but except though we have this limitation, x is not allowed to be 2. X cannot equal 2. All right, so the graph looks just like this, except that x is not equal to 2, except that we can't have a value for x equals 2. Every other number on the graph is going to make the graph look just like this one, except we cannot have a value of x equals 2. So what does that mean for the graph? Well, the graph's going to look like this then. 1, 2, 3, 4, 5. It's going to still look exactly like this, except we can't have a value at x equals 2. X equals 2 would be here. There's x equals 2 right there. So if we draw the line, it would look something like this. But now when we get to 2, we're not allowed to have a value there, right? So we're going to have the little hole. There's going to be an empty hole right at x equals 2. Okay, there's going to be a little gap in the line. Numbers can get really, really close to 2 in both directions. So it could be like 1.999, and it can also be 2.0001. Numbers on either side of 2 work just fine. And they make the graph look just like this graph. The only thing is, at exactly the point x equals 2, we are not allowed to have a value. Okay? And so it causes this hole to happen. Okay, so before when we talked about we said, well, look at this. You know, wouldn't this have a vertical asymptote because it has this x minus 2 on the bottom? That's what we said with vertical asymptotes. Vertical asymptote was numbers that aren't in the domain. A little fine tuning of that, okay, is that numbers that aren't in the domain when we're in lowest terms. Okay, we have to get lowest terms of the fraction. Okay, so we have to do lowest. So if we were to graph this, we'd have to look at lowest terms first. Okay, so here, if this was the original function, we'd say, okay, can anything cancel out? Can we get in lowest terms? In this case, yes, we can. Cross it off here, cross it off here, and then now this would be like our lowest terms, and we'd have a hole at this point. Okay, now once we got in lowest terms, if we had something in the denominator, then that's where we'd have a vertical asymptote. But when we cross things off like this, if we have any factors that can cross off and reduce like this, that's where we end up having the hole in the graph. That one place in the graph we're not allowed to have a value in it. All right, so next time what we're going to do is we're going to take all these things and put them all together and finally graph these things. All right, but for now, just take that, and I'm sure we can have lots of fun with that. All right.